So because of this, these scatterings are essentially non-relativistic. And if you do the kinematics, you can show that 2 is twice un v cos theta, where theta is a scattering angle. And ER, the recoil energy of the nucleus, this is a recoil kinetic energy, is just q squared over 2mn. So this is our setup. And the thing we measure, or the thing we hope to measure, is a scattering rate of nuclei. And to compute that scattering rate, we need to convolve the scattering cross-section with the velocity distribution of dark matter. But the thing for us to compute as dark matter theorists is the scattering cross-section of the dark matter chi per unit energy on the target nucleus. And this is going to involve 3 steps. The first step is interactions of dark matter with the nucleus at the level of elementary particles. The first step is to figure out the coupling of the dark matter to QCD stuff, so quarks and gluons, because the quarks and gluons are the things that make up primarily the nucleus. This is the first step. The second step is going to be an intermediate step, and the intermediate step is going to be to convert the chi QCD coupling into a coupling between the dark matter and nucleons. So by nucleons, I mean protons and neutrons. And of course, protons and neutrons glomp together to make nuclei. So the third step is then to convert this chi-nucleon coupling into a chi-nucleus, coupling, and this is the thing we actually want for our detector. So these 3 steps can be, well, the first step is kind of happy in the sense that we know how to deal with elementary particles. The second and third step get consecutively trickier. And the second step involves the physics of hadrons, so the physics of QCD at low energies. And the third step involves a bit of nuclear physics. So fortunately, most of the nuclear physics has been worked out by other people. I'm not an expert on nuclear physics, but we can essentially appropriate some basic results here. There's some interesting low-energy QCD results in this step, but I'm going to go through to show how you start from an elementary particle coupling and work your way down to the actual cross-section. The other thing is, in terms of notation, I'm going to use little n to refer to nucleons, and I'm going to use big N's to refer to a nucleus. And the notation for a nucleus is a nucleus has some total atomic number Z, it has Z protons and A protons plus neutrons. So in other words, so you probably all know this, but I'm just reminding you if you haven't seen any nuclear physics. So this will be our notation, and it's a standard notation. So as far as the quark QCD couplings, the picture of dark matter we have in the back of our minds, the one that in some sense motivates this story, is WIMP dark matter. So dark matter with a mass in the order of a few hundred GeV or so. And in this case, for dark matter mass of a few hundred GeV, your recoil momenta are roughly order of 100 MeV, and the recoil energy are something like 100 keV. So these energies are all very small compared to the mass of the dark matter particle. And in the case of a WIMP, the interaction is mediated by typically either Higgs or a weak vector boson. And these are much heavier than the momentum transfer and the recoil energy. And that means that instead of worrying about interactions between, let's say, quarks with a Z and then dark matter with a Z and connecting them up with a propagator, we can instead just write an effective 4-fermion coupling, assuming the dark matter is a fermion, to describe the interaction. So at the end of the last class, I spoke about 3 classes of operators that are looked at a lot. We have our so-called scalar-scalar operators. We have our vector-vector operators. Oops, sorry, I should have a and we have our axial. So for example, a scalar-scalar operator could be generated by, this kind of scalar-scalar operator could be generated by exchanging a Higgs. This kind of vector-vector operator could be obtained by exchanging, let's say, a Z, and so too could the axial. And the reason for dividing up the operators into these different forms is that, it turns out that these two operators end up coupling effectively to the net total number of nucleons in the nucleus, whereas the AAA operator effectively couples to the spin of the nucleus. So I'll come back and discuss those. But for this reason, these two operators are sometimes said to be spin independent. They just couple to the total number of nucleons. Dependent. And this one is said to be spin dependent. So you'll often hear about people talking about SI or SD scattering, and that just corresponds to spin independent or spin dependent. Okay. And then when I write an operator, what I secretly mean is a term in the effective Lagrangian for the theory. And in the effective Lagrangian, the full structure of the operator, the full operator should have mass dimension 4 to appear in a 4-dimensional Lagrangian. And that means that these couplings have dimensions of 1 over mass squared. And this makes sense if you think about their origin. So for example, if I think of the SS operator as coming from the exchange of a Higgs, let's say QQ, the effect of integrating out the Higgs, so at the fundamental level, I just have a chi-bar Higgs-chi coupling and a q-bar Higgs-q coupling. But in the limit when the momentum transferred here is small, I can shrink this propagator to a point, and I get I get this effective vertex, and the effective operator I get is going to be a Yukawa coupling to quarks, a Yukawa coupling to chi over m Higgs squared times q bar q chi bar chi. So this is the effective terminal Lagrangian that you get by integrating out the Higgs. And this is a good approximation as long as the effective energies in the effective energy transfer in the reaction is very small compared to the Higgs mass, which is the case here. Okay. So the next step is, given these effective operators, and of course there are other kinds of operators you can have, but the other kinds of structures that you would expect typically give you smaller cross sections. So these specific examples are the ones that are considered in most detail. I'm going to go through each of them separately. I'll start with the spins, the scalar-scalar, then vector-vector, then axial-axial. And these two cases will be fairly similar. This one will be a bit trickier. So let me start off with the scalar-scalar operator. So I'm going to assume that I start off with an effective Lagrangian that contains a bunch of terms. So I'm going to assume that it contains some contributions corresponding to light quarks. So by little q, I'm going to mean the light quarks. And by light quarks, I mean up-down strange. In principle, I could also have couplings to heavy quarks. And I'm going to call the heavy quarks big Q, Q bar Q, chi bar chi. So the big Q is charm, bottom, or top. And then I'm also going to have this coupling to the gluon. GA, GA, U nu, chi bar chi. So to start off with, so in some sense we've done step 1, and we want to go to step 2. But before I actually do step 2, let me pretend instead that I'm just scattering off a quark. So this isn't really quite justified because at these low energies, I can't think of quarks as free particles because we know that quarks end up getting confined. At high energies, I can talk about quark scattering, but at low energies, it doesn't make sense. But for now, let's pretend that the quark is just some free particle with mass mq. And I'm going to look at the contribution of this operator to dark matter quark scattering. So if I take this operator, I can compute the dark matter quark scattering with a Feynman diagram obtained from the Feynman rule for this interaction. So the Feynman rule for this interaction looks like this. So this one vertex has the chi contracted with itself on it, and the q contracted with itself on it. And this corresponds to some matrix element. And this matrix element turns out to be, there's a constant kappa that I'll tell you about in a second. I get a factor of dq from the vertex. And then from the fermion lines, remember, I get spin polarizations. So if I call this P3, if I call this P4, I call this P2, I call this P1, I get spin polarizations for the chi. And in this case, it's just U bar 3 U1. And then I get spin polarizations for the quark, which is U bar 4 U2. So is my notation consistent with what you saw in field theory, basically? So in principle, I should write, like, let's say, U of P1 in S1, but I'm just abbreviating all that as 3-1. OK, so this is my matrix element. And let me remind you that when you compute a matrix element, through the Feynman diagram involving this operator, this corresponds, in fact, to an operator expectation value that you go off in Fourier transform. So what this corresponds to is a final state where I have Q of P4 and chi of P3, where I sandwich the operator dq chi bar chi, q bar q, and then here I put a q of P2, chi of P1. So this scattering matrix element corresponds effectively to this operator matrix element, where I take the operator and I plunk it between this final state and this initial state. Now, there's a slight cheat here because this operator is actually a position space operator. And what I actually mean when I write this is take the position space operator, evaluate it at a point, Fourier transform the whole thing with respect to the position. So in other words, take a d3x e to the I k dot x. And when I do that, and I contract up this and that, what I get is this. So this is just a different way of writing what you're actually doing secretly when you compute this matrix element for scattering. Yes?
So if I treat those operators as kind of operators for P2, then I would get the left hand. Would I get the left hand side? But would I get the K?
Oh, so I'll come back to what the kappa is. So actually, this is kappa. Okay, maybe this is a bad.
Yeah, well, no, I understand.
Okay, so this is a lowercase k, and that's a kappa. So I'll tell you what the kappa is in a second. Okay, but remember, when you compute this, I don't know how you treated it, but you can think of this as, for example, for this matrix element, I contract up this operator part with this q, and I contract up this chi with this. I contract up this guy with this, and I contract up this guy with this. And these contractions give me these spin polarizations. Is this how you did it in QFT? OK. And then these q's contract up, and I get spin polarizations, at least after Fourier transforming. Now, this kappa piece, I haven't told you what it is, but what this kappa piece is it turns out that it's equal to either 1 or 2. And it's equal to 1 if chi is a Dirac fermion. And it's equal to 2 if chi is Majorana. So you probably dealt with Dirac fermions in your QFT course. You may not have dealt with Majorana. So the factor of 1 is what you're probably used to. Now, it turns out that if chi is Majorana, A Majorana fermion is a fermion that is its own antiparticle. And when you have a field that is its own antiparticle, that means that I actually get a second contraction. So normally I'd identify chi with a particle and chi bar with the antiparticle. But for the Majorana state, I also identify the particle with the antiparticle as the same thing. So that means there's also a second contraction. And the second contraction would be actually contracting this guy with this and this guy with that. So that second contraction would give me a factor of 2. So that's why I stick in a kappa here, just in case I want to consider the case where dark matter is a Majorana fermion. So again, you're probably familiar with the 1 case. The 2 case is just stick on the factor of 2, just because there's a second contraction. Okay, so I have this result, and I'm going to often write this result. I'm going to match it up to this matrix element, this operator matrix element, and secretly I'm always going to Fourier transform it, even if I don't actually write it. So just keep this in mind. Okay, so in any case, this is my scattering matrix element, and I can take the scattering matrix element, and if I wanted to compute a scattering cross-section from this, what I would do is square the matrix element, and then sum it over all the final spin states and average it over all the initial spin states. And that summed and squared matrix element is a quantity that I'm going to call m squared with little brackets around it. So the m squared is just square it in the usual sense, and the brackets mean that I'm secretly doing the spin average in sums. So this is the summed and squared matrix element. And when you do that, it's straightforward to get that. This piece is going to give me, I get Dirac traces, and I go through the usual procedure, and you'll know how to do that. Now, if I take that matrix element, and I evaluate it in the non-relativistic limit, by non-relativistic limit, I take into account that the masses here are much larger than all the momenta. The leading term in the non-relativistic limit turns out to be kappa squared dq squared times 4 mq m chi squared. So this is what I get calculating this diagram, treating the quark as a free field with a mass mq. So again, this is just completely straightforward. It should all be familiar to you. But I'm going through this because the next step is going to be to connect that to nucleon matrix elements. And that's going to be our step 2. So I'm just putting this, I've gone through this, which should be very familiar, just to warm up to the nucleon case, which is actually going to be basically the same thing, but with a slight twist. Okay, so that's our step 1. Our step 2 is to match this onto a nucleon matrix element. So in other words, suppose instead of scattering with a quark, what we scattered with instead is a nucleon. So this would actually be a real physical process because we can have free nucleons at low energies. We can't have free quarks. So this first case is just kind of a pretend warm-up, but let's actually do the nucleon case. So the nucleon case goes through in basically the same way, but there's one slight twist. And the slight twist is, well, let me just go back to this contraction of the matrix element. For this contraction of the matrix element, when I go through everything, effectively the quark part and the neutralino part, the quark part and the dark matter part factorize. In that I could have written this thing as Q4, Q bar Q, Q 2, with a chi 3, chi bar chi, chi 1. So the structure of this, the fact that I have Q's and chi's and Q's and chi's, they don't talk to each other. So in principle, I could factorize these two pieces and write this matrix element and that matrix element, and I get the same answer. So the reason I wanted to mention this is that we have a result for nucleons. Now, this is a non-perturbative result that is typically derived from lattice QCD. But this non-perturbative result is that if I take the matrix element with an outgoing nucleon with momentum P4, and I stick in a Q bar Q operator in between, and I take an initial state with a momentum P2, and when I do that, and I take this matrix element it turns out that what I get has the following form. FTQ of n u bar 4 u2 in the non-relativistic limit. So non-relativistic limit means p4 minus p2 squared, much, much less than the nucleon mass. So this result, it's a non-perturbative result. It's something you can't just sit down and compute Feynman diagrams to get, but it's what comes out. This diagram, this result just takes what we had before and decorates it. And the decoration is just that factor. So if we had a Q of P4 and a Q of P2, and we could treat the quarks as free particles, this matrix element would just give us a U bar 4 U2. But because we now have a nucleon here and a nucleon here, we end up decorating it with this extra factor. So that means that if we wanted to compute instead the scattering of chi with a nucleon, we could go through the same procedure, do this factorization, but now instead of having quarks here, we'd have nucleons. And the nucleon, QQ bar nucleon, with the DQ factor going through that whole business, my amplitude would be now I have a nucleon interaction, QQ. This matrix element would now be instead, I'd have the same kappa from the contractions of nucleus. I'd have the DQ overall coupling. I'd have this decoration factor, Mn over MQ, FTQ of n. And then I'd have my, where are we? U bar 4, U2, U bar 3, U1. So we could actually go off and calculate the contribution of this operator to the nucleon scattering, just like we did for the quark scattering. And the only change, at least at low momentum, would be this decoration factor. So this is actually a nice, handy result, because this means that if we start off with this Lagrangian, with, let's say, so far I'm only considering the light quark operators. If I start off with this Lagrangian, with these quark operators, I can convert this into an effective interaction between the dark matter and I can convert this into an effective interaction between the dark matter and nucleons directly, in the sense that I can write this result. I would get the same result if I had the effective Lagrangian of, instead of having what I had before, instead if I had the effective Lagrangian dq mn over mq fn tq times, instead of having q bar q, instead I have an n bar n operator chi bar chi. So you can think of the contribution of each DQ piece as a contribution to the effective nucleon dark matter operator with this coefficient. So what we've done is we've gone from an effective quark level interaction to an effective nucleon level interaction. Yes?
So are we replacing all those first, the sum, all those first three terms by this, or each of these by? Is there some over Q? That's what I want.
Okay. This is just a contribution from the light quarks.
Okay.
So in other words, what I should really do is, instead of just taking a single DQ, I should sum this over Q equals U ds. So the effective coupling would be the sum of stuff. So now this is only the contribution from the light quarks. I'll also have a contribution from the heavy quarks and a contribution from the gluon. So that'll be my next step to address those. But at least the contribution to the effective interaction from the light quarks is going to be the contribution from each of these operators, but I have to sum them up. So I have to sum up all the possible contributions from my quark level Lagrangian to the actual nucleon level Lagrangian. Yes?
Can I just clarify? So you wrote F with the TQ subscript?
Yes?
What's TQ? So and different F
Yeah. So this Fn sub Tq, well, first of all, it's just a number. It's a dimensionless number. So for example, I would have I could have a. So for example, if I take my nucleon to be the proton, and I take my light quark to be the up quark, I'd have some number for this. And then I have, let's say, some different number if I took the nucleon to be the neutron, and I took the light quark to be the strange quark.
Sorry, I should rephrase my question. What is the T there? You know?
It's just notation. So this is just some number, and that's part of the name. So it's just a conventional naming. I don't know why they put the T on. Okay, but these are just dimensionless numbers, and they've been computed by people on the Labus, and you can go look them up. So that means that what I start with in my fundamental theory predicts the values of these DQs. And once I have the values of those DQs, I can convert my interaction from the fundamental theory into an effective interaction with these DQs now with nucleons. And let me also apologize at this point. When I write n here, I mean nucleons generically. But what I secretly mean is you'll have a contribution for n of either the proton or the neutron. So I'm kind of abusing notation. I'm using n to be either nucleon or specifically the neutron. So here, what I should really write is I have some effective coupling to neutrons and another effective coupling to protons. And in general, the FTs for protons can be a little bit different than the ones for neutrons. It turns out numerically they're pretty similar, but they can be different. So sorry about my wacky notation, but I think this is also fairly common. Yes?
So to clarify, on the top line, the subscript n in there refers to nucleon, either protons or neutron.
Yeah.
And the sum in the effective Lagrangian should be over n as well, as in should be sum over all protons and the neutron.
Yeah. Well, so I've written one term here, but there will actually be two terms. There'll be one term for the proton and one term for the neutron. So think of this as the contribution. Okay. Yeah, I'm kind of cheating on the notation, but I should really write this as I have one coupling to neutrons and some possibly different coupling to protons. Okay, so at least we've dealt with the light quarks. The next step is to deal with the heavy quarks and the gluon. So it turns out that this isn't quite as bad as it might seem. So we have this. It turns out that there are a couple of there's some nice tricks for the heavy quarks and the gluon. So let me move to that next. Okay, so we have this result for the light quarks. It turns out that there's a similar result for gluons. And the result for gluons at low momentum transfer is G mu nu A, G A mu nu, n of P2 is, in this case, just some number. And this number is written conventionally as so this piece is just some number. That's no problem. And then we have the same polarization spinors. So that means that if we want to connect up the gluon to an initial state, the gluon just contributes an effective coupling like this. And just like we did for the light quarks, we could write in a gluon coupling of the same form. So we could write an effective contribution of the gluon coupling to this kind of operator from this. So in other words, this result, I can recast this as a contribution to LF. And the contribution to LF from the gluon is going to be, I'm going to have my dg from before. And then I have my minus 8 pi over 9 alpha s. And again, because the polarization spinors at low momentum transfer just correspond to what I would have for an n bar n operator, I would just have n bar n times chi bar chi. So the contribution of this gluon operator, even though it looks a bit messy at the start, I can reduce it to an effective operator between nucleons and my dark matter. And again, I'll have one term like this for protons and one term like this for neutrons. And these couplings are computed on the lattice. And it turns out that these couplings are not actually independent of the other ones. You can actually show that the gluon coupling, Fn of T sub g, and you'll actually do this in the homework, is 1 minus the sum on Q equals UDS of F sub T sub Q of n. So in other words, if I know these three numbers, I don't have to compute a separate FTG. I can use this relation to extract this from that. Yes?
So I guess here, because of, like, there's an 8, so we have some vertical group.
Well, no, this 8 just corresponds to how I normalize this. Oh, sorry, this A. Yeah, so here, this A and this A, so this is the adjoint index of the gluon?
No, I was thinking of the 8.
Oh, that 8. Yeah, no, that 8 isn't necessarily related to the gluon sum. It's just part of how we name that. So there'll be a reason for that you'll see down the road, but it's just part of the naming convention. Okay, so I've dealt with the gluon piece, and effectively this gluon contribution will sum with the light quark sum, and I'm going to get some total effective coupling, but I still need to also figure out the contribution from these heavy quarks. So for the heavy quarks, I'm running out of Blackboard space. Let me zoom up. For the heavy quarks, it turns out that what ends up happening is, remember, the typical energy in this event is very small. And the typical energy in these events is much smaller than the mass of the heavy quarks. And whenever you're only interested in physics at energy scales much lighter than the particles that are involved with it, you can, just as we did for the Higgs or the Z, you can integrate out that heavy physics and recast that contribution of the heavy physics in terms of an effective operator. And that's what we can do with the heavy quarks. So the heavy quarks, a heavy quark could connect in to my dark matter this way. So if I was only computing scattering of the dark matter with the heavy quark, this would be the end of the story. But I want to connect these heavy quarks with the nucleon. And the nucleons, if you recall, essentially only contain the light quarks. The nucleons essentially only contain the light quarks, or as that result shows, some gluons. But what we can do is effectively integrate out these heavy quarks. And we can integrate out these heavy quarks because they're going to connect up with the nucleon through a loop that connects it to a pair of gluons. So I've got gluon here, and this is going to connect up with the quarks in a nucleon. And it turns out that the effect of integrating out these quarks is to take the heavy quark coupling and turn it into an effective gluon coupling. Because I've closed this loop, and I've turned the heavy quarks into something with two gluons coming off. And you can show that the effect of that at low energies is you take your QQ bar operator that we had way up there, and you just replace the QQ bar operator with minus 2 alpha s over 24 pi, 1 over mq, GA mu nu, GA mu nu. So the factor of alpha s here comes from the fact that I have two values of the strong coupling here. I have a loop factor. So the loop factor is this. And the 1 over mq, the mq effectively comes from doing the loop integral sum. And if you notice, the dimensions work out. Remember, this combination is mass dimension 3. This combination of gluons is mass dimension 4. So the dividing by the 1 over mq gets me the right mass dimension. And physically, we also expect 1 over MQ dependence in the sense that if these quarks become really, really heavy, we would expect the effect to decouple. So that means that this combination also has the right decoupling behavior as we expect. So this is nice. Because we can replace Q bar Q by this effective gluon operator at low energies, we're basically done. This thing is just going to contribute to the effective DG coupling. And we know how to handle the DG coupling through that effective Lagrangian. So now, when I take all this stuff and I plunk it together, if I started off with that effective Lagrangian at the top right there, I could replace all this by an effective coupling of dark matter to nucleons, and I can write this as Fp, P bar P, plus Fn, N bar N, where these Fps and Fns are given by, so here N's a neutron, here N is either a proton or neutron, sorry again. These Fn combinations are just given by these results. I have a contribution from the light quarks of my usual FTQ of N, and then I have a DQ over MQ, and then I have the contribution from the heavy quarks. And the contribution from the heavy quarks, when you work out and simplify everything, you get a sum over the heavy quarks, C, TB, FTG of N, DQ over MQ. And then finally, I have the pure gluon contribution, 8 pi over 9 alpha S, DG, Fn, T sub G. So this is the whole effective interaction induced by this QCD stuff for the dark matter to couple to protons and neutrons, specifically for the scalar operator. So this is straightforward. We take our fundamental theory, we take our underlying theory of dark matter. That tells us what the DQs and the DGs are. And then we just look up these numbers, the FTQs, and the FTQs give us the FTGs. So we look up these, plug them in, plug in the masses, and I come up with effective couplings, Fn, that give me my effective couplings here. So if the only thing I wanted to compute was a coupling of my dark matter to free nucleons, I'd be done. But there's one more step. So the one more step is to convert this effective nucleon coupling into an effective nucleus coupling. Now, before I do that, let me just mention that if I start with this interaction, suppose I compute the scattering cross-section. For the scattering cross-section, the result is straightforward. So suppose I was scattering off, let's say, a single neutron. If I was scattering my dark matter off a single neutron, my matrix element computed from this would be of the same form as the matrix element I computed up here, except now my spinors would correspond to the final initial neutron states. And my result for the squared matrix element would be exactly the same form as this, except now instead of having a DQ squared, I would have an Fn squared. And instead of having an MQ here, I would have an Mn. So now I can take my summed in squared matrix element, and I can plug it into my formula for cross sections. And what I would get for that would be just a d sigma n dq squared. And when you work through all the factors and so on, you would get a kappa squared over 4 pi. You would end up getting a 1 over v squared. And you would get an Fn squared. And that's the whole story. So if I want to compute the scattering off a single neutron, this is what I would get. If I want to compute the scattering off a single proton, I just replace Fn by Fp, and I'm done. OK. And again, this Q, remember, this Q is a momentum transfer. Q is just the magnitude of the outgoing spatial momentum of the nucleus, which in my notation here is P4. So Q is a momentum transfer, and that's just equal to the spatial momentum of the outgoing state. because we're assuming that the initial state is at rest. So in other words, Q is P4, and this is equal to P4 minus P2, which is equal to the P1 minus P3 by momentum conservation. So this is the momentum transfer, and this is the momentum transfer we were talking about. And if you wanted to, we could convert this into a d sigma n dE recoil using the fact that the recoil energy for the nucleon would be just q squared over 2mn. So I could change a q squared to an ER by multiplying this thing by 2mn. Okay, that's good. But unfortunately, we need to do one more step because our detectors, for the most part, aren't just built out of free neutrons or free protons. Instead, they're built out of heavy nuclei. And we'll see why they use heavy nuclei in just a second. So to convert to heavy nuclei, what do I want? We need to pull one more trick. So the one more trick to convert this to a nuclear cross-section, this is our step 3. It turns out that this conversion is really easy in the limit of q squared goes to 0. And for the nuclear cross-section, if I scatter off a nucleus, the result would be d sigma n dq squared, specifically at q squared equals to 0. This turns out to be the easy case. You can show on the nuclear physics side that your effective p bar p or n bar n operator just counts the number of nucleons within the nucleus. So at 0 momentum transfer, you can identify these with, in a non-relativistic limit, you can identify these with a proton number and neutron number. And the effect of each of the individual protons in the nucleus and each of the individual neutrons in the nucleus, when I compute the amplitude with the nucleus, is just going to give me a sum of terms, one from each nucleon that I just add up. But I add them up at the level of the amplitude. So when I square the amplitude to get the matrix element, I'm going to get a coherent enhancement. So put another way, my scattering cross-section off a nucleus is just going to be kappa squared over 4 pi, same as before, 1 over v squared. But now instead of having an fn squared or an fp squared, I sum over all the contributions to the amplitude from each of the constituent nucleons. So what I end up getting is I have z protons in my nucleus, and I have a minus z neutrons in my nucleus. And each of them contributes individually to the amplitude. And they all contribute individually, coherently in the limit of q squared goes to 0. And that means that when I square the amplitude to get the matrix element, I get a square of this. And all this stuff adds coherently. So this is specifically in the limit of very low momentum transfer. And you can think of low momentum transfer as the effective wavelength of the dark matter being very large. And when the effective wavelength of the dark matter is very large, you don't see the individual nucleon structure of the nucleus. You see the whole thing together. And that's why you get this coherence. Now, at non-zero momentum transfer, the effective wavelength, if you like, the Compton wavelength of the dark matter becomes smaller. And it turns out that at higher momentum transfer, you can start to probe the individual nucleon structures. Yes?
Sorry, I'm a little confused with this notation. So suppose I have a particular nucleus with Z proton and A minus Z neutron.
Mm-hmm.
So would there be a term, like you said there's a sum, is that just these two terms or like
Oh, well, the sum is the factor of Z. So the point is there'll be a contribution to the amplitude from each of the individual protons and each of the individual neutrons. And when you add up all those contributions, each proton gets the same contribution, Fp. Each neutron gets the same contribution, but there are A minus out of them, and there's Z protons. Yes?
That looks like you're including interference between scattering off the proton and scattering off the proton, right? Like the cross term.
Oh, yeah.
But isn't that, they're distinguishable, right? Whether you scatter off a proton or a neutron. So why would you interfere those?
Oh, but so the point is that at low momentum transfer, you don't actually probe that interior structure of the nucleus.
Okay.
So at low momentum transfer, your effective Compton wavelength of the dark matter is very large. So you don't actually see the inner structure of the nucleus. So you actually can have interference. Because each contribution just contributes individually to the amplitude.
Yeah, so that is the point you're making.
Yeah, exactly. That there is this interference, and it turns out that numerically in a lot of theories of dark matter, we actually have Fn equal to Fp. And if Fn is equal to Fp, this just becomes an A, and I get an A squared. And if I have a heavy nucleus, so for example, xenon is one popular target nucleus. Xenon has an atomic number, an atomic mass, an A value of about 130. So 130 squared is like 20,000. So I get a big enhancement for heavy nuclei.
But this is different from deep inelastic scattering, which is the opposite scenario where you can resolve the...
Exactly. Yeah, so in deep inelastic scattering, my energy is large compared to essentially the bound state energy. So I start probing the underlying structure. Yeah, so the fact that I square the neutron and proton stuff together is a fact that I don't resolve them, and see them. Now, we also need to account for the fact that as I turn up the momentum transfer, I am going to start to resolve stuff, and I'm going to start to lose coherence. Now, I guess a fully proper treatment of this, for fully proper treatment of this, requires some nuclear physics. So I'm just going to essentially quote the result. But the result is that d sigma dq squared at finite momentum transfer is just given by the value at zero momentum transfer, but multiplied by a so-called form factor. So remember, ER is equivalent to Q squared, up to a 2n factor. So this thing is a so-called form factor. It's related to the Fourier transform of the nucleon density within the nucleus. And this is something that you need to go to nuclear physics to get. But for most of the spin-independent scattering we're going to do, a good approximation for this form factor is a so-called Wood-Saxon form. And that is that Fn squared of ER is given by 3J1 of QR1 divided by QR1 all squared e to the minus q squared s squared, where here s is roughly 1 Fermi, and R1 corresponds to an effective size of the nucleus, given by R squared minus 5 S squared, where R is roughly the nuclear radius of about 1.2 A to the 1/3 Fermi. So remember, a Fermi is 10 to the minus 15 meters. And so where this comes from, well, so this is accounting for the loss of coherence. The actual form here is something you get out of nuclear physics. It's related to the Fourier transform of the nucleon density within the nucleus. And it turns out that you can show that in the limit of ER goes to 0, corresponding to Q squared goes to 0, this thing just goes to 1. On the other hand, at large momentum transfer, you get a suppression. And the suppression takes into account the loss of coherence, the fact that your dark matter is starting to probe the internal structure of the nucleus. Yeah, and so the J1 here is a spherical Bessel function. So again, it looks essentially like, I think it's actually 3 sine QR over QR. No, sorry, I think it's just 3 sine QR. Or sorry, in the limit of small QR, it's roughly 3 sine QR. And at larger values, it oscillates. Yeah, so this is just your spherical Bessel function. So we're now basically done. We start with our theory of dark matter, which gives us the coefficients dq, and dg. We go through this whole song and dance. We convert them with some numbers, the FDQs and the FGs, and this gives us an effective Fn and Fp. Now, then we compute the amplitude, the matrix element, and this gives us our d sigma n dq squared, which I can convert this into a d sigma n der, which is the thing we're going to use eventually, by just multiplying both sides by 2mn. Just using the fact that er is just q squared over 2mn. So this is my result for the effective spin-independent scattering cross-section. And the reason we call it spin-independent is that this coherence factor doesn't care about the spin of the nucleus. It just adds up the number of the number of nucleons. And one other thing I want to mention, and we'll come back to this, it's also common to define an effective scattering cross-section, an effective total scattering cross-section of the nucleus. This isn't actually the total scattering cross-section. What it is it's essentially you integrate over all possible values of dq squared from the minimal value, which is 0, up to the maximal value, which is 4 mu n squared v squared. And the thing you integrate is d sigma n dq squared evaluated at q squared equal to 0. So the actual total cross-section would be this thing, but as a function of q squared. But this effective cross-section, I take my d sigma dq squared, but I evaluate it specifically at q squared equals 0, do the integral, which is just equivalent to multiplying by 4 mu n squared v squared. And what I get at the end of the day is just a kappa squared over pi mu n squared z fp plus a minus n, or a minus z fn squared. So this, if you like, is it's not the actual total cross-section. It's sort of the cross-section I would have if my form factor were equal to unity. And it turns out that this quantity will be useful for comparing different experimental results on direct detection. So this is just some dumb definition that happens to be useful down the road. OK, so this is the story for the scalar-scalar operators. Yes?
Can I clarify that mu n is the mass?
So the mu n is the reduced mass of the dark matter nucleus system. So mu n is the reduced mass. So it's mn m chi over mn plus m chi. And in fact, suppose I look at the limit where my dark matter is heavier than the nucleus. In the limit where the dark matter is heavier than the nucleus, I get a cancellation. The denominator is essentially m chi. So my mu n asymptotes to mn. And mn is roughly a times mp squared. And if I have fp equals fn, this factor gives me an a squared relative to what I would have for a single nucleon. And this factor would also give me an a squared compared to what I would have for a single nucleon. So in the limit of heavy dark matter, I actually get an a to the 4th enhancement. So I can get a very, very large enhancement for heavy targets. So a lot of experiments that look for this kind of scattering use very heavy targets. OK. So that's everything for the scalar-scalar case. Let's see what I want. That front one's supposed to come down, sorry. OK. So let me go on to the vector-vector case. The vector-vector case is actually basically equivalent to the scalar-scalar case, but with a slight twist. So for the vector-vector case, we have these operators. And the Qs here could be heavy quarks or light quarks. And suppose I was to go through the same procedure and just look at quark scattering with the dark matter in the same limit, treating the quark as a free particle. It turns out that I would get the same, I get a slightly different matrix element. I would get my M to be a BQ U bar 4 gamma mu U2 U bar 3 gamma mu U1. And this is the whole story. So you may be wondering why I don't have a kappa. It turns out that you can show that if chi is a Majorana fermion, gamma mu chi bar gamma mu chi is equal to 0. So and what ends up happening is, remember, the chi bar, in a sense, is equivalent to the chi. And when I contract through with the gamma mu, I end up getting a cancellation between the left and right-handed pieces. So this VV interaction only applies to Dirac fermions. And this is a matrix element I would get from this, treating this as a free quark. And the summed and squared matrix element that I would get out of it turns out to be just BQ squared times the same thing I had before. When you do all the spin sums in the non-relativistic limit, this is what you get. So I get essentially the same result I had before, except without the kappa. Yes?
So what are we integrating out here? Vector protons?
Yeah, so this kind of interaction, you would expect this kind of interaction from integrating out a Z, for example. So the Z will actually give you VV, AA, but also VA and AV. But the AV stuff is subleading. And the VV, in terms of interacting with the nucleus, doesn't interfere with the AA. So this decomposition is orthogonal, if you like. So this result, the basic result here, gives me the same summed and squared matrix element, treating everything as a quark scattering. Now we want to convert this into a nucleon scattering, and it turns out that doing this is easier for the vector case than for the scalar case. And the reason for that is that if I look at the combination Q bar gamma mu Q, this is equivalent to J mu Q, which is the Q number current. And what I mean by the Q number current is that J mu equals 0 of Q, J0 of Q, is the number density of Q minus the number density of anti-Q. So you can think of this as the net Q number current in the sense of particles minus antiparticles. And similarly, J of Q is the net Q number spatial current. Now, this is handy because this number current is related to the electromagnetic current. So the total electromagnetic current corresponding to the symmetry of electromagnetism turns out to be the electromagnetic current is just the sum over all the charged particles of each of their individual J mu's. So in other words, if I sum over everything, J mu EM, this is just a sum over all standard model fermions, QF, J mu F. And we know that the electromagnetic current is conserved. Now, if we apply this to a nucleon, the nucleon has the net quantum numbers of up, up, down, or up, down, down. And because of this, when we apply this relation to a nucleon, we only need to worry about the up and down quarks, and all the other quark combinations vanish. So taking this together, I'm running out of space. Let me just try to move this up. the upshot of this, I guess I'll have to come back to this on Monday, is that only the net contributions of the up and down quarks matter, and my effective vector-vector interaction turns into a q bar gamma mu q, fp, p bar gamma mu p, plus fn, and my fp is just the sum of the contribution from up quarks, which I have 2 up quarks in the proton plus 1 down quark, and my fn is just 1 up quark plus 2 down quarks. So the fact that the vector coupling is related to the electromagnetic current means that contributions, let's say, from a strange quark, the proton doesn't have any net strange content. It has some bubbling mass of strange and anti-strange, but the net sum of those of the contents is 0. So the only thing that gives me a non-zero contribution are the net up quark and down quark parts. And that means that I have very simple forms for FP and FN. And I don't have to do this fiddly, complicated QCD stuff. OK, so I've gone a bit over. So I'll come back to this on Monday. You have a new homework. It's on the website. And I guess you have a tutorial this afternoon. And I guess that's all I have for now.